we're now going to examine some of the exact values that you get with trigonometric functions for angles that pop up really commonly like these. Now, these come about from some really common sorts of triangles. If we have an isosceles triangle here that has a right angle in it, that means both of these sides are the same length. Now, just to make the simplest one possible, I've given them sides of 1. How do I go about finding this side? We're doing trig, but still Pythagoras comes in handy. 1 squared plus 1 squared, if we call this c, equals c squared. So 1 plus 1, that's 2. And taking the square root of both sides, notice that this is a length, so it can't be negative. It has to be positive. So there's no point saying plus or minus the square root of 2. We just say it's the square root of 2 because it's a length. So we can now put that in on our drawing. And looking down at this other triangle, you might say, hold on a minute, it doesn't have a right angle, but it will have a right angle if I drop a vertical line straight down from the top. Now, if this is an equilateral triangle, let's give it sides lengths of 2. That way, when I split this one in half, it'll have 1 and 1. Now, if I want to know what the length of this side is, again, I can use Pythagoras because now I have a right angled triangle. So I can say 1 squared plus, let's label this h for height. 1 squared plus height squared is equal to 2 squared. Tidying this up, that means 1 plus height squared is equal to 4. So my height squared must be equal to, subtract 1 from each side, 3. And taking the square root of each side, h must be equal to the square root of 3. Again, it's a length, so it doesn't need to have two answers here, plus or minus. So I can replace that h with a nice confident root 3. All right, how does this help? Well, this helps because we know two of the angles in this particular triangle. We said that it is isosceles, we said that it is equilateral, so we know that this is 60 degrees, and we've halved this angle exactly, haven't we? So that makes this angle 30 degrees. Okay, I've made a bit of a mess of my picture, but there we go. What about this one up here? The gradient of this line, rise over run, is 1 over 1, which is 1. And that tells us that this is actually a 45-degree angle. We also know that because both of these angles would be the same, so to add up to 180, it has to be 45. And this is going to help us. We'll just rub out some of our working here if you've got this down. Actually, I can just leave it there. No, I'll rub it out because we need some room to do some thinking. All right, as we go to write our sine of theta, cos of theta, and tan of theta trigonometric functions, remember with these, we always write down an equation. So if we're figuring out, let's say, the sine of, we'll start with 30 degrees, then we know that with sine of theta, we need to do opposite over hypotenuse. So here's 30, its opposite side is 1, over the hypotenuse is 2, and we get half. So I've put a half in the box there. All right, now if I was to work out the sine of 45 degrees, I'm going to use this picture because I've got a 45-degree angle. And again, sine of theta is opposite over hypotenuse, so I have 1 over root 2. And if I want to figure out the sine of 60 degrees, again, I'll find a 60-degree angle, I'll use this picture, and I'll say it's opposite over hypotenuse. So that's given me these three parts of my table here, and we're going to put this in a table just so it's easy to memorize it, because all of these are really handy to memorize. Now, do you get them on your formula sheet? No, you don't. Your formula sheet in your HSC contains these two pictures, but it actually just has them really simply. So this bottom one, it just has this triangle written down like that, and then you get this triangle written down. So you can easily figure these things out if you need to, but that time that it would take to flip to your formula sheet and work it out, somebody else who just knows off the top of their head that the sine of 30 degrees is half, they've already solved that one and they're on to the next question. So memorizing these is a real time saver. All right, we've got the sine of each of those angles. Now, what you'll notice here is that for the cos column, if I know the sine of these three, I actually can figure out the cosine of that angle really, really simply. Now, cosine is adjacent over hypotenuse. So if I'm doing the cosine of 30 degrees, then instead of doing, have you noticed that sine of 30 opposite over hypotenuse, that's the same as the cos of 60, adjacent over hypotenuse. And that's because this side over here, it might be adjacent to the 60, but it's opposite the 30. And both of them are over the same thing, that same hypotenuse. So you'll notice that if you've already found these ones and memorized them, we've got half, 1 on root 2, root 3 on 2, and you need to just say that over and over. Half, 1 on root 2, root 3 on 2. Half, 1 over root 2, root 3 on 2, and you just memorize it. These ones go back the other way because the cos of 60 is the same as the sine of 30. So half, 1 on root 2, root 3 on 2. It makes sense that the cos of both of these, as cos and sine of theta with 45 degrees, is exactly the same, because whether you've got opposite over hypotenuse or adjacent over hypotenuse, they're the same as each other. So now we just need to figure out the third column, which is tan. Now if we have the tan of 30 degrees, then tan is opposite over adjacent. So our 30 degree angles down here, we have opposite over adjacent, 1 over root 3, and I've written that in our table. If we want to find the tan of 45 degrees, that's nice and simple. It's just 1, because opposite over adjacent, 1 over 1 is 1. And the tan of 60 degrees, let's go down to our 60, we have opposite over adjacent, root 3 over 1, which is just root 3. Now these three are quite easy to remember because these two really just look like that one split up. 1 over root 3, then we have just the numerator from here, the 1, and then we have just the denominator. So memorizing these on their own, 1 over root 3, 1, root 3, they sort of come together quite easily too, I think.